Hi, this is a video on the Gauss's Law packet. So let's just take a look. At the top, we've got Gauss's Law, and it reminds you that we're picking our Gaussian surface, so that E is constant on the whole surface and it goes through the point where you want to know the E field. Cool. So before we get started, let's remind ourselves we're going to need these little pieces of information as we go on. The surface area of a sphere is 4 pi r squared. The surface area of a cylinder, and in particular, it's a cylindrical shell is what we're interested in, is 2 pi rl. The volume of a sphere is 4/3 pi r cubed. And the volume of a cylinder is pi r squared L. Those will be useful for us. Okay, so the first question is find the electric field inside and outside of a charged isolated conductor with a total charge plus Q. So the first thing we need to do is say what kind of symmetry it is. It is spherical symmetry, so therefore we need a sphere as our Gaussian surface. Okay, I'm going to change here. So we want to know the electric field inside and outside. Cool. Inside. Inside, it is a conductor, right? If it is a conductor, then we know that the Q is 0 inside. Okay, so that's going to be something that we think about. So if we want to know somewhere inside, so we pick our Gaussian surface. It has a radius r. Okay, so this is our cutout, right? Our two-dimensional cross-section of our sphere. Okay, so we start with this. We start with Gauss's law. Now, we have picked our Gaussian surface so that the electric field is constant. So we can pull it out. And here's the deal. What is Quincke? What is the enclosed charge in here? Is there any charge in here? No. So this side is 0. It means there is no flux going through this Gaussian surface. So even though, you could keep going, and that's 4 pi r squared, and that's E, that E is going to be 0. And if you go back to when I first talked to you about conductors, I said that the electric field inside a conductor is always 0. And I said I would prove it to you later when we did Gauss's law. Well, here it is. Your proof that electric field inside a conductor is 0, and that is a direct consequence of the fact that you cannot have charges inside. All right.